Okay, so we are ready. I have, for those of you on WebEx, we have muted your phones, just so you know. Today's session is on transformers, their application, and their protection. Welcome to this session. My name is Thomas Dimitrovich. As you know, I've been communicating with everybody out there already, and I just put this up as it's my basically. I'm a member of of various committees with NFPA. I'm on UL standards, and I'm on some other types of reference materials and industry standards. I am I'm speaking on behalf of myself. I'm not speaking on behalf of any code making panel members, NFPA, or any organizations. Everything that you hear, is my own opinion, just for your information. I just saw a note on the YouTubers, my intro. That is Bill. That is me on the guitar, buddy. In fact, I made that entire intro on Apple's GarageBand. So I did the drums, I did all the different guitar pieces, and just overlaid them. So anyway, today's session is on transformer applications and protection. So welcome to this session, and I'm excited about it. Transformers are all over the place. We do a lot with transformers in power distribution systems, and it's really important that we take care of those devices, and we know how to properly apply that equipment and provide protection for it. So I've got 2 hours, and we're going to dig into, try to understand as much as we can in 2 hours on transformers. So the first part, see, for those of you who've been in this before, I've forgotten about this quiz at once, and that will never happen again. We will, Chris. Yes, I'm going to put that quiz up right, I believe, now. So here we go. There's the quiz. All right, so we're going to walk through this. We had a good number of people viewing this. Control 1 and Control Q. So it looks like most of you know what a transformer is, except there's one guy or gal who was probably just trying to be funny, but that's okay. That was a, whoops. That first one was a give me. 174, okay, 162 did this one. So this is a secondary full load amps of a 3-phase 480 volt 208 volt transformer. It's 139 amps. What is the primary full load amps? And I put this one on there because I wanted to see what you guys and gals knew about the turns ratio, and you did great, because the right answer is 60.23. How we get that answer for the 11 and 29 for the so we got about 40 others. For the 40 other people who didn't get this answer right, we take that 139 secondary amps, multiply that by 208, divide that by 480, and that tells you what that is reflected to the primary. And I don't have to go through KVA and all this other good stuff. That turns ratio is an important tool that we need to understand, because we will use that in various times. From a power distribution analysis perspective, we will use the turns ratio of a transformer to solve some problems quickly. In any case, and you may not be able to just do the full load amps and whatnot. Hopefully, we may or may not be able to get to that. If you took my selective coordination class 2 or 3 weeks ago, the 2-hour session on there, I talk about selectively coordinating around a transformer, and that is really when this turns ratio comes in handy, at least one of the applications. Primary full load amps of the following transformer. All right, so this was a little bit of not a trick, but it's a real world application. And if we get through the 2 hours at the end, I do have a transformer, which is this transformer. 3750 is your KVA without the fans. What the fans will let you do is push that transformer beyond its standard normal 3750 kVA, I can pull more power through it. Now, many, if not all of these that I've ever seen are a, are a constant kVA. So I'm sorry, they're basically your kVA is increased, but your voltages haven't. So you still have the same voltages. You've just been able to pull more power. So 3750, I can get 5,000 when I have the fans added. The 694 answer there is with the 5,000 kVA. And if I'm sizing overcurrent protective devices on this transformer, I'm going to need to make sure that I consider pushing 5,000 kVA through that transformer. That's what you paid for the fans for. That's probably what you paid extra for in that transformer. So the you've got to account for that extra full load amps when you're sizing your overcurrent protected devices, or you will trip that you could trip that overcurrent device. So in any case, I would say both of those answers, 52694, are probably right, depending upon what you're doing. But I would lean more towards 694, especially when you're talking about overcurrent protection and things of that nature. You're going to need that 5,000 kVA number. Secondary full load amps, same deal. If I've got 5,000 kVA and I've got the same voltages, I still got 480 volts on the secondary, but I'm just loading that transformer up. I have to calculate my overcurrent protection and things of that nature around the around that higher 5,000 kVA, because that's the capability. So that's the 6,014 number. So you 84, I'm with you. You 54, I know you're probably going, I don't agree with him, but you can. Everybody has their opinion. So in any case, that's okay. For inrush, is it a 3750 or 5,000 kVA? Your inrush, I would use the 3750 primarily because your inrush is really around the magnetics and whatnot of that transformer. When you plot your transformer damage curve, it's more than likely going to use that 3750. That's more of a magnetic responsibility of the makeup of the equipment without the load. Remember that your inrush current is no load applied. You're just energizing that transformer. So and the other thing that it doesn't, which I have a question in here somewhere, or it's in the PowerPoint, but the fans do not change the impedance of the transformer either. So your calculated fault current on the secondary, if you're doing an infinite bus calculation for the secondary, you're going to be basing that calculation on that 3750, not the 5,000, because your percent impedance and whatnot is based upon the 3750, not the 5,000. So it's not going to impact the fault current on the secondary of that transformer. All right, good dialogue there. What is the primary full load amps of the following transformer? 30 kVA. That's AA primary. We'll learn what AA means. At the higher kVA, doesn't it have a higher percent Z at that kVA? Kevin, no, it does not. You remember, percent impedance of that transformer is dictated by the iron core, the physical construction, and obviously mechanical or the electrical performance of that. But it doesn't have anything to do with the load. It's we get those values, short circuit testing, open circuit testing, and things of that nature on the transformer. So your percent impedance, and I'm going to show you a nameplate to solidify that in your mind and support what I'm saying. The nameplate value for that transformer has both KVAs, both full load amps, all of that information, but only 1% impedance. And that's because you can't change that physical construction. That's why your inrush current's not based upon the fans and whatnot. So it's just the way that puppy's made. All right. So on this one here, looks like I ran through some of I did do a couple of these numbers in the few minutes I had before this meeting, because again, I don't know if everybody was on. I accidentally deleted the slides on my slide deck that answered all these questions. But in any case, that's fine. I calculating. You guys did a great job in calculating this. I'm not going to walk through this calculation because I'm going to teach you how to do this calculation. So for the 23 who aren't sure, the 11 and the 4, I'm going to show you how to do this calculation during the slide deck. So I'm not going to do that right now. And majority of you, more than a majority, know how to calculate full load amps on primary and secondary. And this is a three-phase transformer. So me and the square root of 3 never got along well with each other in school. I would go to parties. Square root of 3 would stay in the dorm. Sometimes the square root of 3 would go to a party and I'd be in the dorm. So I never could get the square root of 3 right. And you got it right on this one. So that is a good thing. And then I threw in a single phase transformer in here as well. So this was a single phase. And I threw some answers in there that are three phase. So if you grabbed that square root of 3, so you 11 that grabbed the square root of 3, you probably shouldn't have done that. But this is that's a single phase, and majority of you got that right. And we're going to walk through the answers on this one when I do the class. I'll tell you how to do that calculation. Secondary full load amps of a single phase transformer, and you got this one right too. So good job for all of you 137 out there. 138. Good job. 139. All right. What is the primary full load amps of the following three-phase transformer? 75 kVA, 480 volt delta, secondary. Okay. And this again, your guys are, I did this training class a couple times out in person, and I added more full load amp examples because this question, nobody knew how to calculate full load amps. Everybody just relied on, well, the full load amps is printed on the transformer. And that's ungood. You gotta know how to do this fundamental, and it looks like everybody online got it. So I'm not going to belabor that point. And again, this is the secondary. So good job, 126 of you. Throw me a bone, you 19. We're going to teach you how to do that in this class here. We're going to give you the math and the examples. All right, so this is the infinite bus short circuit current calculation, and how you do this is basically you take 1388, you take the full load amps of any transformer, divide that by the impedance, multiply it by 100. So I take 1388, divide that by 4%, and then multiply that by 100, and that is my maximum three-phase bolted fault current value. And if you don't know what per unit is, you just did it. If you've never heard per unit before, that tool that power system engineers use, you just used per unit if you did that calculation. So congratulations, you are now a per unit guru. So the 34.7, you guys, 88 of you got it right. 29 that didn't have enough information, and 38 that didn't have a clue. And those 20,000 amperes group, we are going to help you out during this class, hopefully. Adding fans to a transformer increases the kVA and available, not available, but available short circuit current on the secondary. I can't spell. Available. And I copied this from a while ago, so that's been up there a while. And the answer to that is false. So 87 of you guys got it right. Adding the fans, you can increase the kVA, but we do not calculate the fault current on the secondary. We do not calculate the fault current on the secondary based upon that higher kVA rating, based on our earlier discussion. Hopefully that helps you out. 500 kVA, 4% impedance transformer with secondary main, maximum overcurrent protective device. All right, so remember, maximum overcurrent protective device. Now you look at this one here, we need to spend some time on, and I do an example of this. I run through a transformer. We're going to do a 112.5 kVA transformer, and we're going to pick the primary and secondary overcurrent devices, primary and secondary conductors, And you know what? We'll do an arc flash study too. I give various options. We do the maximum and we plot around the inrush current, and I'll show you some of the TCC curves that help you understand that protection level. But on this one here, so here's what we do. The maximum, remember, is that 250% based on the table, which we're going to go over all this. The full load amps on the primary of this is 601 amps. If I take 2.5 times that, I get 1,500 amps. Now, because I'm at 2.5 times, I can't go to the next higher, which would be 1,600. I got to drop back. I cannot go to the next higher at 250%. Now, you'd say, well, who in their right mind would size the primary overcurrent device to 250%? Why would you do that? The answer to that is you may have to do that. And the reason is because you may be selectively coordinating through that transformer, and that primary breaker or fuse is going to have to not trip on downstream faults, on that through fault. And if you did not take my selective coordination class a couple weeks ago, you might want to go back and review that video, because I talk about selectively coordinating through a transformer. And I'm telling you, not too many people do that. Not too many people even think about that. They selectively coordinate on the secondary, they selectively coordinate on the primary, and they completely forget about coordinating around that transformer, because a transformer doesn't stop what it's doing just because a fault is on the secondary. It does the same job. The right answer on this is 1,200 amps, not 1,600 amps, because if you're at 250%, the table, and we're going to review that table in our system in the class. You can't go to the next higher. You've got to go to the next lower. So 1,200 amps would be the answer that you'd need there. And again, I'm going to do 112. I'm going to do a transformer example, and we're going to calculate everything we need to know. We're going to beat that transformer up. So, and the principles, once you do one, in my opinion, you're pretty solid on all. You got the basics down. So this is a primary overcurrent protected device of 1,200 amps, 80 foot of conductor, and secondary main, minimum primary conductor ampacity. If I've got, and I was in a class one time, and I had like 86 people in the class, and I put this question up, and everybody said they took, I think the 600, I can't remember which one of those numbers is the full load amps times 1.25, and that's what they all picked. Out of 5 guys in the class, I had 86 people, 5 guys picked 1,200 amps, because, 240 tells you need to protect a conductor at its ampacity. And sometimes we will say, look, I've only got 300, 400 full load amps on that primary. Why the heck would I put a 1,200 amps worth of conductor and a 1,200 amp breaker on there? That I'm just looking at a note on the chat session. Somebody says, I don't necessarily agree that you are calling us a guru. There's more to per unit impedance than you're exactly right. I was being facetious, Mr. Fontaine. Yes, there's a lot more to per unit than just doing that calculation. So, but in any case, again, we're going to cover this and in detail. But you got to protect a conductor at its ampacity. All right, so this is 4% maximum overcurrent protected device on the secondary. Okay, so now this is I'm going to have to get my calculator out because I'm not sure if I did these. So maximum is 1.25 times the secondary full load amps. So I got a 500 kVA transformer. Divide that by square root of 3. Divide that by 0.208. That's 1387. 1.25 times, that's 1734. I can go to the next higher, actually, and I would probably go to a 2,000 amp. So I can, on the secondary, go to the next higher, and we'll talk about that in the table. I'm not going to look at it right now. We're going to go through that detail. I would say you could do a 1,600 amp, and that's probably what you would do, but you could put a 2,000 on there too. All right, we're going to go through this in detail for at least one transformer. With a primary over 1,200 amps and a secondary main of 2,000, minimum conductor ampacity on the secondary. Oh, I love it. 2,000 amps. You have to protect that conductor And again, there's requirements. You get into the TEP or the transformer secondary conductor rules and things of that nature. So 2000 amps, that's the right answer on that one. All right, you get the green thumb. Nope, that way. There it is. All right, that's the quiz. That's all I have to say about that. Well, that was fun. So, and now we're going to get into our program. I'm going to just, before I get into this, I'm just going to take a look. When I teach, remind people that each phase has a limited amount of current. This is especially useful on a high let when people tend to overload two of the three. What was the registration Menti code? Registration 341007. Okay, if you don't like using the square root of 3 for a three-phase transformer, just divide the kVA by the 3 and use the line to neutral voltage. There you go. You see that? I'm telling you, there are more than one way to skin a cat, and you've taken care of that. You know what I typically do is and I'll show you my equations. I take the kVA divided by 3. I multiply that by the square root of 3, and I divide that by the line-to-line voltage. I take the long way around to account for that square root of 3. So if I look in the National Electrical Code for the definition, in 450.2, there's a definition for a transformer, which I think violates the NAC style manual because it uses the word transformer in the definition. I might propose something for this, but anyway, it says an individual transformer, single or polyphase, identified by a single nameplate unless otherwise indicated in this article. I guess that's not going to disagree with that one, but I personally hold on. I got to get my PowerPoint. There it is. I sort of like this, an electrical device that transfers energy from magnetic induction from one circuit to another. And usually the voltage and current are transformed from one level to another. And I say usually because in some cases you can have a one-to-one transformer. That's I can have a 480 to 480, and I would do that to knock down fault current. If I want to, if I just need to knock down my fault current for selective coordination reasons, for short circuit current rating, interrupting rating, whatever that reason would be, I may use a 1-to-1 transformer instead of a three-phase transformer. Give you the whole screen. Okay. So if you look at this transformer, I've got my coils, my primary and secondary windings. I got a core, which basically that's that big hunk of metal in the middle. I've got a frame holding it all together. I need to have ventilation. The air will naturally flow from the bottom up through, and the top is open on these transformers. And you want to keep them open. You don't want to block them. You don't want to be, I don't even think I put the pictures in here because I don't even want to promote what they do. They use them for storage, right? Ventilation, you have the enclosure. So that's basically your transformers. You got step up, you have step down, you have one-to-one, isolation transformers, auto transformers, single phase, polyphase, three-phase, harmonic transformers. You have high efficiency transformers. For a static type of device that just sits there, no moving parts, there's a lot of options. And they use them in many different applications for control power inside of power distribution systems. I mean, there's transformers down at very, very low voltages or for transformers for your doorbell in your house, right? So transformers are all over the place. It's amazing what you can do with a little wire and some iron, When you get into the big boys, you've got your dry type, which is probably the majority of what you see in power distribution systems. And then you have you always got to worry about cooling. Transformers do what they do, but they do generate heat. And you do have to deal with that heat. And the big transformers will use oil and other types of media. They'll use fans. They'll force the oil through, etc., to cool that transformer. We're going to talk about the different ways that we address that. But you have your liquid type and your dry types. Those are the basic two things that you have. Then connecting the transformers, I can connect the transformer in multiple configurations. Delta to delta for an ungrounded system. Again, If I corner ground that, I can mid tap that. There's different things I can do. Essentially, when you see a delta delta, you have an ungrounded system, and that's what we used to do back in the day, well back before my time. Ungrounded systems, and then you have the delta Y, and what we're very familiar with is a delta Y ground. So when you ground XO, the transformer basically establishes a ground for the facility. You have that grounded conductor. That's like a boat in the water. When you don't, the delta delta is a boat floating in the water, and the waves will just bounce it around. That's the voltage. Your voltages will go crazy during events. The moment you cast that anchor, which is your ground, your XO, you take your XO and you drop that anchor off, and you basically create that reference point for the power distribution system. Very effective at what it does, but it does increase your fault currents. There were benefits for a delta delta in that it was a very stable. That first ground fault's a gimme, but that second one's a doozy. And but anytime you had you would lose a lot of motors and things of that nature due to transient over voltages in those delta ungrounded systems. That's why they sort of corner grounded those delta systems. Say, hey, I'm gonna establish a ground, and they started that by corner grounding it. They created the zigzag transformers to ground power distribution systems because they wanted that anchor for that boat, so they didn't have to worry about all those surge voltages. But again, they sidestepped one problem, which was the over voltages, but then they created the other problem, which was high fault currents when they grounded that system. But we learned to deal with that. And then you can, you have your Y deltas. Again, that's your ungrounded and effectively grounded sources. You see these installed with mid taps on the ground when you ground one leg when supplying combination 3-phase, single phase loads, etc. 25 kV, 35 kV. So, these are, they may not be very common in a normal power distribution system, but they're not also uncommon in other applications where they're very well suited. YY connections, you don't see too many of those. So those are just different ways. And what this is showing you is that the transformer is an important piece of the power distribution system because it establishes your grounding. It establishes your voltages from line to line, line to ground. It is a very important piece of the puzzle to creating a power distribution system to serve loads for these reasons. This is where it's done. It's done at the transformer. These are just delta center taps. So again, the transformer is going to establish those second. These are from IEEE standard 141. These are your nominal system voltages that we have. So your 600 volts, 480, 240. But your transformer is going to be used to establish these. And what the design engineer has to do is figure out when they are going to apply what voltages. If it's a industrial facility, I may need only 480 volts throughout my facility. But you're probably, you could say, well, I'm going to use 277 volt lighting and I'm going to limit my 120, but normally you're going to have that 240, 120 volt type of secondary for a lot of different applications. So, but in any case, the transformer is a critical part of the pie. All right, so basic equations. There are some fundamental equations that I think we all need to know and understand, which will basically helps us understand how transformers operate and function. I'm applying a voltage to a coil of wire around an iron core, and I'm inducing a current and flux magnetic components to induce current in the secondary. So I am applying a voltage on the primary and I'm going to have a resultant voltage on the secondary. I'm going to have an inrush current when I apply that voltage. That is based on the characteristics of the windings and the core and et cetera. But I'm going to have an inrush current. I have to deal with that inrush current because it's an absolute, that's like a motor's inrush current. Anytime you deal with coils of wire around iron cores, when you start energizing that, it's going to create a challenge for you with regard to that inrush application. Now, understanding that applying a voltage on the primary, it will induce that voltage on the secondary and it'll drive the load, whatever that load is that's connected. If I don't connect the load, I'm not going to be pushing current to nowhere. I will deliver the kVA it'll deliver more than the kVA. You got to be careful about overloading a transformer, but it will deliver the demand that's placed on it. The fundamental equations that you see up there, I2 over N1, the turns ratio, N1 over N2. Now, this is just a single phase. I'm showing you a single phase transformer with a core. We'll connect these up into three-phase systems, so it gets a little bit different. I mean, you still have the N1 to N2 on every core, but in some cases, like when we did our example, the 480, and we had the 480 volt primary, 208 volt secondary. We didn't take, or maybe you did. I don't know. I don't. I always just take the secondary voltage line to line, divide that by the primary voltage line to line. That's my N2 over N1, or vice versa for N1 over N2. And but sometimes if you're connected delta to Y, if you want to know the turns ratio for each individual transformer in a three-phase system, you're going to have to do the possibly the line to neutral on the secondary and line to line on the primary to get the effective turns ratio of each individual transformer that is connected in a three-phase bank. But we don't typically do that. We take line to line on both sides for our turns ratio. But in any case, these are some fundamental equations. Also, we can translate those. Once you have three sets of equations like that, we can use our calculus and we can arrange these in different ways so that we can see what the primary current is based upon the secondary current. So remember that one of the questions in our quiz was if I gave you the secondary current and I said, what's the primary current? What's the primary full load amps, I believe is what I asked you, and I gave you the voltage ratio. So I gave you V1 over V2 line to line, and I gave you I2. This is how they calculated I1. They took the secondary full load amps, multiplied that by the secondary voltage, and divided that by the primary voltage, and that gives them the primary full load amps. I can do that with any current that I see. If I measure current on the secondary of that transformer, I can multiply that by the turns ratio, and it will do its job. It'll do what it's been designed to do and relate that current, and it'll be smaller on the primary than on the secondary. If you have remember, going from a lower voltage to a higher voltage, the current will go down. So if my secondary is 208, my primary is 480, I'm multiplying that by 208 divided by 480, so my number is going to be smaller on the primary. But if I have a reverse power fed, then if I'm feeding 208 and I'm going to, if my primary and secondary are converse because I'm stepping up instead of stepping down, again, it just follows that basic principle. The higher voltage will have a lower current than the lower voltage because it's the same amount of energy that you're transmitting. And then I can do my voltage as well. My voltage on the primary is is the secondary voltage times the primary. So it's an inverse. It's not V2 over V1, it's V1 over V2. So if I took, for example, if it's a 208, 480 over 208, right? 208 times 480 divided by 208 is 480. Boom, it just falls out. But now if my voltage was not 480, right? If my voltage was a lower voltage because that's my system voltage, I would still use the turns ratio, which would be your 480 to 208 to figure out what my primary voltage is based upon the secondary actual voltage. So again, the turns ratio is a tool, and understanding those basic fundamental equations are important for a lot of different things. Understand your taps, understanding short circuit currents on the secondary, things of that nature, reflecting currents from primary to secondary. That's all the ways, and you'll never know the application. Various applications will present you where if you understand these principles, it'll make your life easier. So again, remember those basic equations. And remember this, this was our secondary full load amps, was 139 amps. What's the primary? And this was the math. I just took the 139 amps times 208 over 480, and I got 60.23. And that's all we have to say about that. So those are just some fundamentals. I didn't get into some of the other equations because I don't know that you really need. I don't want to clutter. You don't need to clutter your mind with stuff that you're not necessarily needing. So in any case, and we'll talk about the full load amps and all the other good stuff. So we're going to go through an example. What I did was I picked 112.5. So what I originally did was I picked a 300 kVA transformer, but I couldn't find a nameplate of a 300 kVA transformer. So I modified the entire presentation last minute to include 112.5 because I found a picture of, I didn't want to do a 30 kVA or a 15. I had the smaller ones. I thought this was a good example. So we're going to walk through this example from soup to nuts. So the transformers are rated in kVA, and kVA is kilovolt amperes. That is when we're sizing the transformer. Now, I should have put a code question to ask what section in the NEC do we use that says that a transformer has to have a kVA rating greater than the connected kVA. I don't know if anybody online. I'm going to put that out there. So I'm looking at the chat. Does anybody want to take a stab? Oh, does anybody want to take a stab at what section in the code? Thank you, Eddie. Eddie got it right. He sent it to me privately. There is no NEC requirement around sizing a transformer for the load. We have requirements that tells you need to have the right size conductor. We have requirements that says you have to have a generator to supply the load. We don't have anything. We don't have anything that says that a transformer has to be sized for the load that you're going to connect. Now we use Article 220. And what from an engineering practice that I am aware of that I know is published in IEEE, I think the Red Book gives us some information around this regard. But we usually will size that transformer about 125% of the load to allow for growth. And there's another. If you look in 220.12. tells us in an informational note that the unit values of table 220.12, which is the general lighting, that says the 220.12 are based on minimal load conditions and 100% power factor, which that is wrong. It's 80. It should be 80%, but in any case, we screwed that up. And may not provide sufficient capacity for the installation contemplating. So one of the things you got to remember when you do your load calculations, and I know there are a lot of people, that say that the load calculations in 220 are inflated, and because of the lighting loads, because of the square foot calculations, etc. But you got to remember, you can't just count on whether or not whether or not you feel that's inflated. You do your load calculations, however you do those load calculations normally. And then what I've seen as an engineering practice is to add 25% because that transformer should have enough for growth in the power distribution system. Now, utilities, Kevin, I know you are right. The utilities love to overload those transformers. So here's what typically will happen. We'll take an installation and we'll design it up. We'll calculate the loads. We'll say I need an X, I don't know. Say I need a 1500 kVA transformer. And the utility may not put a 1500 kVA transformer out there. They'll put probably something a lot less because they'll say he's not going to use 1500 kVA. And you know what? We're going to push that 1500 kVA transformer up to higher. And so the challenge there is if you don't design for that, when they put a smaller transformer in, you still have the same size conductors that you planned for. That transformer is going to have a lower impedance, and your through fault current is going to be much higher than what you expected after you do your analysis. So, I did this. I had a class one time, and I had a utility guy in the course, and he came up to me and he said, "Yeah, we do that." He goes, we know they're not going to use whatever kVA they calculated because they have the analyses and stuff like that, and the percentage of the transformer main that they have is much less than their usage is much less than what the kVA of that transformer is. And then he said the benefit of that is that they can reduce the conductor sizes, blah, blah, blah. But the problem with it is that utility transformer that they put in is usually, I agree, it's probably smaller because they're pushing it. And the challenge is that I'm not changing my conductor sizes nor my equipment to account for the higher fault currents. But I'm sizing it based upon my load calculations, anticipating that. But in any case, a lot of times you're applying dry type transformers throughout the power distribution system, down further in the system. That's not a utility type of thing. You probably want to plan for some growth. That would be, it's not a requirement by the code. It's probably just good etiquette. All right, so knowing the kVA, here are a few more other good, I debated on whether to put this in my equations section, but I left it down here. This is how we calculate full load amps on transformers, and you'll notice how I did this equation right here. Whoops. This equation, let me do a pen right here. I threw the square root of 3 in the numerator and the 3 in the denominator. And you may say, why the heck would you do that? Because me and the square root of 3 don't get along. I account for it everywhere. So you could simplify this to kVA divided by the square root of 3 divided by the kV. I always throw that in. I say it's kVA over 3 because in my mind I do this. I have a 3-phase transformer. I have to take my kVA divided by 3 because I have 3 single transformers. Then I have to take my kV, divide that by the square root of 3 to get my single phase voltage. So I get everything down to single phase and do my math. Now, you can say I'm crazy, but I don't make mistakes on quizzes. And it works for me. Either way, you may develop what works for you. Now, VA, we size transformers based on VA, not on watts. Okay, so I see this in lighting calculations. I've seen people do this where they talk about watts per square foot, and we have to remember that we use this power triangle. We take watts and VARs into consideration, and we will size our transformer for VA, not for watts, and not just for VARs. So, I can do power factor correction and whatnot. If I do my power factor correction on the secondary, I can say, well, I'm supplying less VA. Again, I know some people that have done that in the past. Supply your VARs locally. You can reduce the size of conductors, etc. But in any case, we size transformers on VA. Calculate your VA. And you're probably familiar with this triangle because that's what, if you were in my class for short circuit calculations, we talked about the power triangle there too. We have resistance and reactance and impedance and how we do short circuit calculations. So there is the kVA has to be on the faceplate of this transformer. It is 112.5 kVA. And again, I do my load calculations and I just determine the size of the transformer that I need. And hopefully plus 1.25. It will have on the label a primary and secondary voltage. 480 volts, in this case, it's 480 delta. And I'll tell you, it's a delta Y grounded system. So 480, 208, 120. Primary and secondary voltages, that's how I'm going to get my turns ratio for whenever I do my math. Depending upon where in the system I am, again, you're going to determine the voltages at each of these buses. The voltage at this bus is going to be determined by the transformer you select there. The voltage at this bus is going to be determined by the transformer you pick there. Also, the short circuit currents, available fault currents, are going to be determined by those transformers. The system grounding is going to be whether or not you have a grounded conductor is going to be determined by those transformers, because these are your separately derived systems. You're establishing your grounding. And there's another transformer down here. So I will have different voltages throughout this system based upon the loads that I'm going to serve. So if you're designing a system, you've got to think about, what am I going to have in this power distribution system? For example, you may sit down and say, you know what, this is a heavy industrial. I'm going to have 4160 motors here. If I designed a system at 480 volts, I'm screwed. I need 4160 volts. I'm going to have to figure out how to make that happen. And I have to, and my transformers are going to determine, I'm going to need those transformers to determine my system voltages to serve my loads. I have potential transformers that I'll use for metering and instrumentation. In all of these in each of these assemblies, I might have a low voltage assembly that has control power transformer in there for control lighting and other controls that are in that equipment. Now I got to think about, all of those transformers need protection. I need to protect the transformer from system issues, but I also need to protect the system from transformer issues. So I liken it to basically these 4 items. I have to provide overload protection, over voltage protection, short circuit protection, and environmental protection. The environmental is following the application. From an environmental perspective, I don't have too many slides. I don't think I have any slides in here. I pulled out a bunch of the stuff around. There's code requirements that tell you you're not allowed to put stuff on top of these transformers, and we just did some changes. They're worried about the ventilation. You're not going to install a transformer that's designed for the inside in the outdoors. So you have to follow equipment ratings, etc. That's all very important parts of this equation. I'm going to focus primarily on your overload and short circuit protection in here. Your over voltage protection, transient voltages, you've got to think about transient voltage surge suppression. And in some cases, you might apply snubbers. There's IEEE papers and whatnot, and there's snubbers that you can buy for help to protect those windings. You got to just make sure that this transformer can take what you throw at it, what the system throws at it, let alone what it can inflict on the system. We will typically, just like a conductor has a damage curve, a transformer will have a damage curve. It tells you how much current you can put through this transformer and for how much time. I'm going to show you plots of this curve. These are taken out of IEEE standards. I believe this is probably out of the Buff book, which is IEEE standard 242. I believe it's also in the Red book, which is, I believe, IEEE standard 141. So in any case, category 1, they'll have different curves for different size transformers and different types. So you have dry type and you have oil type. So category 1 transformer, this is your I squared T curve that tells you how much current will damage that device. These are category 2, and I believe I have a slide in here that talks about each of the categories, what their range is. But in any case, you'll see that there are what they call frequent and infrequent faults. They'll have curves in here based upon the transformer short circuit impedance, which I believe includes the source impedance, and basically that gives you from a frequency perspective, if you have frequent faults, it'll tell you whether or not you're going to damage the transformer. These curves get a little bit more, I would say you get more information based upon the larger transformer. It's just like anything. You buy a very expensive large motor and you're going to have a heck of a lot of data. You buy a little instrumentation transformer and you're not going to have transformer damage curves and things like that, because when they fail, you just, you size it per the code. And if they fail, you buy another one. But if you're going to make a big investment, you're going to be plotting the transformer damage curve. You're going to understand that damage curve with regard to the through fault currents that they'll experience and the overcurrent protected devices on primary and secondary. So this is the damage curve from the 112.5 kVA transformer. It's a dry type transformer. ANSI C57109 is the oil-filled. C5712 gives you your dry type transformers, and they categorize the dry type transformers in categories 1, 2, and 3. I'm just gonna. I think it's in my buff book. I don't know that I think I deleted that slide that talked about categories 1, 2, and 3. Yeah, so a category 1, 2, 3, and 4. They have 1, 2, 3, and 4. Category 1 is 5 through 500 kVA single phase, and 15 kVA through 500 kVA three phase. And that curve that you're looking at right there on the screen is the category 1 damage curve taken from C57.12. So and that again, it's an approximation. I'm not getting that from the manufacturer. I'm taking that from standards. So of course, every transformer manufacturer will have their own. Every transformer will have its own curve, but I'm not going to get that for a 112.5 kVA transformer. I go by these standards, and quite frankly, the actual damage curve is probably further to the right, giving me some buffer. This is a conservatively low anyway. So in any case, what you'll see two things on here. You see the damage curve, and you see another important piece of information, which is that inrush current. Now, the inrush current is when you first energize. Remember, when you're dealing with iron. I don't know. I'm from Pittsburgh. So when you're dealing with iron, your first time you energize a transformer is your inrush current is probably going to be different than subsequent times of inrush currents for that transformer, just because you're saturating that iron and etc. So the inrush current is plotted on this curve, and it can be calculated based upon individual transformers with information that is provided by the manufacturer of that transformer. And again, you get a lot more information for the larger transformers than you do the smaller transformers, just because that's the way it is. Obviously, it's more of an investment. You're buying a 5,000 kVA transformer. You're going to have a lot more information on that transformer and a lot of different ways to protect that transformer than you will on a small 30, 112 kVA type of transformer. So in any case, you have your inrush and you have your transformer damage. I just saw a note. What's a snubber? Don Gannier. I will put some links to snubber technology. And it's like it's a tuned filter basically that takes out that high frequency, that transient voltage that'll occur. And usually you get those transient voltages from fast switching. So I think you probably have more issues when you're using something like a vacuum interrupter to do switching as opposed to some other technologies. But when you're switching that transformer on and off quickly, you can create high voltages. And what we do is we create a filter that basically takes that transient out. Another one, can the curve apply to category 2? So a category 2, yes. You can use that curve. Actually, you know what? Yeah, if you plotted the category 2 curve, that thermal damage curve is pretty much the same. When you get into category 2, you're dealing with the like a K-rated transformer, frequent faults. You have a few more offshoots down the bottom of that, which I think I showed it. Hold on, let me just go back a couple slides. There it is. So, there's your category 2 curve or curves. See those little dashed dotted lines? that takes you're taking the source impedance, you're taking the impedance of that transformer, and again for fault currents from 70 to 100% of maximum possible, you're getting a frequent damage for those another portion of the curve for that category. But for these smaller transformers, and again, category 2, that's what I'm saying. When you get to the larger transformers, you're getting a little bit more information. Category 2 applies from 501 to 1667 single phase and 501 to 5000 kVA three phase. All right, so you have your transformer. So if I'm looking at this transformer, what we're going to do is we're going to walk through what the code says, and then we're going to plot these curves to show you how it relates to what we just saw from an inrush current perspective and from the damage curve perspective. This 112 kVA, 480 to 208, and the percent impedance is 4.17%. And I got that information straight from the nameplate of this transformer. Now we're going to reference 450.3 of the book. Oops. 450.3 of the book, so the great book of the National Electrical Code, tells us that we have to have overcurrent protection in accordance with .3A, B, or C. And again, and then they restate the... so that's why I think the transformer definition needs to change in the NEC. And I don't know if anybody out there agrees or disagrees with me, but I think the generic definition of a transformer transforms voltage, etc. That other definition that I had, and then this would clarify that they're talking about a transformer or polyphase bank of two or more single phase transformers. But in any case, so overcurrent protection again. So transformers over 1,000 volts. So this one does not. This is backwards. And I don't know about you guys, but I always find it odd that as you go through the National Electrical Code, over 1,000 volts is always at the tail end of the section. But in the transformer part, it's the first part. So if you're used to the NEC, it's easy probably to make a mistake to use the wrong table in here because you're used to low voltage is first, medium voltage is second. But in this case, it's backwards. So we're going to have to skip A and we're going to have to go to B. And we go to 1,000 volts nominal or less. Overcurrent protection shall be provided in accordance with the table 450.3b. And again, and there's some other details there. And then C is your voltage, your PTs, your potential transformers. So in this application, we're going to be using table B, and we're going to calculate the full load amps. We're going to apply those multiplying factors. Then we're going to select the overcurrent protected device, and then we select our conductors. And you don't want to make the mistake of selecting the conductors first and then the overcurrent protective device, because your overcurrent protective device on primary and secondary, especially on primary, I'm just going to focus on the primary. You have to account for that inrush current. So they put multipliers in there, because you're going to be bumping that up. You're providing short circuit protection, basically, not necessarily overload protection for that transformer with that primary overcurrent device. All right, so single phase transformer, these are our numbers. There's our equation. I'm going to calculate the full load amps using my primary and secondary. Again, what I'm doing there is I threw you a little twist. I have the 1,000 in the top, but I didn't put it in the second. I should have put it in the second because I got kV. Actually, yeah, no, that 1,000's got to come out of there. Yeah, I screwed that one up a little bit. So that should be, I fixed it in one, but I didn't fix it in the other. Where's my pen? So since I'm dealing with voltage at the bottom, since I'm dealing with voltage down there, I need 1,000. I need this equation up here. I need that 1,000 down here. Now, if I was dealing with kV down here on the bottom, then I wouldn't need that 1,000. I fixed it in one, but I didn't fix it in the other. So be mindful of that. I wanted to make sure it's clear for when they look at the video that they know what's going on there. All right, so primary full load amps. So my primary full load amps is 135.30.32. I take my 112.5 times square root of 3, divide that by 3, divide that by 480, multiply that by 1,000, and I get 135.32 amps. I probably shouldn't go out to 2 decimal points, but in any case, I did. 135 amps on the primary. And my secondary is 312, just basically applying the equations. And there I got the right equations on that one. So 312 on the secondary, 135 on the primary, and that's my starting point. So I need to be able to do that. Okay, so secondary full load amps, 312, primary. And this just shows you about if you're using the turns ratio. If I calculated my secondary of 312, I multiply that by 208, divide that by 480, I get 135.3. If I do it the long way, I get 135.3. So you only need to calculate one time and then just reflect via the voltages. Makes life a lot simpler. They're the exact same answer. And if I look at this this transformer, it's a delta Y grounded system. I got 312.3 amps in the secondary, but notice where my 135.3 is. That 480 to 208 is not the turns ratio of each of those individual transformers because it doesn't account for that square root of 3 on the primary. Remember, the primary is connected in delta. The actual turns ratio of each of those would be a little different if I wanted to do each phase turns ratio. But for this 3-phase bank, I take line to line on the secondary, line to line on the primary, do my reflection, and I'm good to go. All right, so this is table B, table 450.3b, maximum rating or setting of the overcurrent for protection transformers 1,000 volts or less. That's the one that we're going to be using. And if I'm doing primary and secondary protection, and I do talk about primary protection only. We'll hit that after we get through a little bit further here. But 250% is my maximum, and you'll note that you'll note that I don't have note 1 associated with that 250%. To note 1, it lets me go to a higher rating, but I'm not allowed to do that on a 250% when I'm using that maximum. So we're gonna talk about the largest overcurrent device I can possibly put on that transformer. And then we're going to talk about where you'll probably end up doing it if you're not required to selectively coordinate through that transformer. So we're going to talk about picking the primary overcurrent protective device. We take that 338 or the 135 divided by or multiplied, by 250%. I can't go to the 350. For that reason, and we had the quiz question, which we got mixed results on that one. But the reason I can't go and step up is because I am using 250% and I don't have note 1 on that table. So 338, I'm going to step that down. So my maximum overcurrent protective device size on the primary is 300 amps for that transformer. Can't go any higher. The minimum size for that is going to be based upon the inrush current of that transformer. I'm going to show you a 300 amp thermal magnetic circuit breaker plotted against the damage curve. And this would be, permitted by code. But you'll notice, you'll say, well, wow, I'm to the right of that damage curve. And normally that would be ungood. But in reality, you're going to have secondary protection for through faults. And if you have a fault in the coil in that transformer, your circuit breaker, your fault currents are going to be much higher than the instantaneous pickup of that breaker. And it's going to provide short circuit protection for the transformer. But you'll notice how close I am. Notice how close I am. There's your inrush. Okay. you want your inrush current. You don't want this breaker to trip on instantaneous. So if I size this per the National Electrical Code, you would say I have a concern in overloads in this region, which after we select the secondary breaker, my argument would be you're protected from overloads due to the secondary overcurrent protective device. But for short circuits, you're going to clear that fault fast on instantaneous. Now that's a standard thermomagnetic breaker. Now, if I put an electronic trip breaker, now I'm going to show you that I get a lot better protection of that transformer, because my electronics, now this is a 400 amp frame turned down to 300 amp trip. So this is my I've got an Optum 550 on here. I just picked, it's a KD breaker. I just picked the Optum. I could have picked a Digitrip RMS trip unit. No matter what, once you get into an electronic trip unit, the value is this knee right here. Okay, that is the value that you have, and I'll show you in SKM that adjustment can go up and down, and I can actually get that conductor protected much closer to that inrush. And I'll just pull this up real quick to show you. I'm going to show you the SKM curves of that same plot, but this includes the downstream breaker. But this is the upstream breaker we were just talking about. I can move this short time delay up or down, and you'll notice if I put it on its lowest setting, which we ship these things at their lowest setting. And you know what happens? When we ship these, right? People don't set them in the field, and this breaker could trip on inrush, because the inrush current's right here in this short time delay. It can trip anywhere in between these this time band, and then if you're not smart enough, then you may not realize that you need to make an adjustment, and you shouldn't just make that adjustment on the fly. You should be plotting that curve and understand that that fault current, that inrush current needs to be below this. It usually lasts around 0.1 seconds. I don't think you're going to have it. You could be a little bit longer, but it's probably going to be lower. Every transformer is going to be different. That's the other challenge. Every transformer is going to be different. The rule of thumb that we use is the inrush current for 0.1 seconds. Could it vary from that? Yes. Could it vary every time you energize it? Probably, depending upon the closing angles and everything else that you have with your system. That's probably a worst case scenario, 0.1 seconds. You just want to stay above that. So, I could put this down and it may not trip, and it may trip, at a future time that I energize that transformer. You just want to keep it above that inrush, because that's a data point that we have based upon standards for that equipment. And then I can modify this curve, and I am to the left of that transformer damage curve. And this would let the transformer energize, and I don't have to worry about selectively coordinating the secondary with the primary. So having an overlap is not bad. It's actually it'll provide lower incident energy on the secondary side of that transformer, because you'll get this primary breaker to trip and open. And we'll talk about that once we get through some of these examples. But in any case, that's sort of what's going on in that diagram. All right, so that's a 300 amp electronic trip unit breaker. Now, let's say, for example, that I got primary protection. I could say, you know what? Look at this. I don't want to put a secondary breaker there. I'm gonna size that primary breaker to 125%, and it tells me that I could go to the next size higher, right? So and then now I got to think about note 1, and I got to think about note 2. Note 2 says where secondary overcurrent protection is required, the secondary overcurrent device shall be permitted to consist of not more than 6. So this just basically is a 6 disconnect rule. At face value, I'm thinking maybe I do 125% primary protection and not put a secondary breaker. Is that an option? Maybe, maybe not. Let's talk about it. So if I go 125%, I'm at a 1.25 times 135.2, which puts me into 169, which means I could probably put a 175 amp overcurrent protective device, because that's the next one higher. And if I put that one in, now I'm still not, I'm close to the inrush current, but I'm, I'm not too bad. I fit that breaker fits nicely in between the thermal damage of the transformer and the inrush current. So that one seems to be a better protection for the transformer, definitely. It'll trip much faster, and it'll let the transformer energize. If I take that same philosophy of 125%, and I could actually use I put 125 amp fuse, which is much less than what I could have done. I could have put a 175 amp fuse there, but I plotted the FRS class K5 125 amp fuse, and it fits nicely, and it provides very nice protection for that transformer, and will still let my inrush current flow. So I could use a 125 amp fuse instead of 175 amp. So you think, hey, that's even better. Maybe I don't have to have that secondary overcurrent device, because now I'm even lower than the 125%. But in reality, although that table tells you and it implies that you can use 125%, I've got two notes in here that I need to investigate a little bit more. I've got a panel board on the secondary, so I go to 408. 408 tells me that in addition to 408.30, a panel board shall be protected by an overcurrent protective device having a rating not greater than that of the panel board. A device shall be located within or at any point on the supply side of the panel board. And if I go to 408.36b, supplying through a transformer, now that's getting really specific. It tells me when I have a panel board supplied through a transformer, the overcurrent protection shall be located on the secondary side of the transformer. So it's telling me that I have to put that overcurrent protection on the secondary of that transformer, with one exception. I can protect it based upon the on the supply side, the line side of that transformer, as long as I'm in accordance with 240.21c1. And if I look at 240.21c1, this talks about location in the circuit for overcurrent protection. And specifically, if I look at C, transformer secondary conductors, it tells me that the conductors supplied by the secondary side of a 2-wire single voltage secondary, or a 3-phase delta connected transformer having a 3-wire single voltage secondary, shall be permitted to be protected by an overcurrent protection provided on the primary. So, I've got a delta Y ground system, and I don't meet any of those allocations. Now, there's I think another application, which I have some of the other language in the from the book that talks about it. The transformer, I'm not going to be able, I'm going to have to supply a secondary overcurrent protective device. That's where I'm going to be at on these transformers. It's very hard and very limited applications where I am not going to have a secondary main providing protection. And again, I'm getting my overload protection from that secondary device for that transformer. Outside, overload protection could also come in the form of not overloading the transformer from a load perspective, just on how you size the transformer. But in any case, that secondary, I'm going to have a secondary breaker, and let's talk about sizing the secondary overcurrent protective device. So I have primary and secondary protection. I'm allowed 125%, and it references me to note 1, which tells me I can go to the next higher. So if I do the math, I'm at 390 amps with 1.25. I'm going to be able to bump that up to 400. So I could technically supply a 400 amp panel with that secondary overcurrent protected device with this transformer, 112.5. And the minimum size overcurrent device, again, that's going to be dependent upon the panel board. I mean, if I put a 112 kVA transformer in there, and I could say I'm going to put a 200 amp panel board in there, and that's all I'm supplying. That secondary transformer secondary conductor is going to be 200 amps worth of conductor. If it's a 400 amp panel board, then it's 400 amps worth of conductor. And I'm going to put a 400 amp or a 200 amp overcurrent protected device because 408 tells me I need to protect it at its ampacity. And then the 240, Article 240 tells me that I need to protect the conductor at its ampacity. So the conductors around this transformer are a little different, and the protection is a little different than how we do things normally. Because normally we would size the load, size the conductor, and then pick your overcurrent protected device. In this case, I'm sizing my equipment, picking my overcurrent protective devices, and then I'm picking my conductor sizes. Now this is this primary and secondary circuit breakers. These are two thermomagnetic circuit breakers. I have a 300 amp, which is the maximum I could possibly have on that transformer. And I have a 400 amp panel board, which is the maximum that I can put on the secondary. So what that's telling me is, you would not typically plot these when you're buying a 112 kVA transformer. You would more often than not, you're going to be getting into this level of detail on larger transformers. But what this does help you see is the protection of a 112 kVA transformer and the ampacity or the overcurrent protection and where they respond or where they lie with regard to two key points of that transformer. One is the damage curve, and one is the inrush currents. So if I, for example, use an electronic trip unit on the primary and a thermomagnetic circuit breaker on the secondary, again, these, I don't have to worry about coordination. If I take out the secondary, if I take out the primary, it doesn't matter. It's just nice to have, it's nice to have that overcurrent device. I could increase the long time pickup and make these align, but providing good protection of that transformer is an important part of that pie. Now this is different. Again, this is an FD circuit breaker, thermomagnetic circuit breaker, sized at 175 amps. So I'm not at the maximum size, and I have a secondary fuse. So that FD breaker gives me a good coordination with the transformer damage and inrush. And my secondary fuse will give me some good protection, and I don't have to worry about coordinating those two together. These are fuses on the primary and secondary, and how they respond or how they relate to the damage and inrush currents, and both of those are nicely paired. Okay, so now I've picked my overcurrent protected devices. I got a 300 amp, and this is the maximum sizes. I have a 300 amp breaker on the main. I've got a 400 amp breaker on the secondary, and now I'm going to be moving into sizing my conductors. But before I do that, I'm just going to check out chat. All right, I'm going to scroll up. You guys are awesome because you guys are sharing information, and I love that. Thank you very much. I learn a lot from some of these things too. Yeah, yep, David. I put the tape on, and I very lightly put it on. All right, any folks getting sound? Hopefully you can. I can't hear anything either. Call in again. Mine dropped. Okay, and call back, or you can check out the YouTube. You can check out YouTube as well. So I am just going to go through some of these questions. For inrush, is it 3750 or 5000? I think we answered that one. You do your inrush current at 3750. I'm just going to scroll down here. Okay, that works. Thanks. You're welcome. I do not necessarily agree with the fact that you are calling us gurus. We already talked about it. So I'm looking at old ones, old tweets. I'm going to page down. Okay, I have a PI. All right. Someone is going to put a public input. Thanks, Eddie. It's a good idea. Put a public input in and say, hey, how do you think that transformer should be sized? I think it's been tried before, but it's always good to discuss. Now, oh yeah, so that's another good point that is made. I will have requirements that tells me how to protect my conductors and size my conductors around that transformer based upon load calculations, right? That may drive a little bit around and between the percentages of overcurrent protection and how I deal with my conductors. That may get you somewhat into the ballpark to help you not screw up. But okay, Tom Arns. All right, utility companies can design around diversity of the load. Yep. I'm not sure about that. Wait, aren't small dry type transformers typically 100% rated for continuous loads? That's an interesting point. So I don't know of anything that says I can't use a transformer at its kVA. There's no 100% rated transformers. There's 80% rated transformers. I use a transformer at its kVA. I can use a transformer above its kVA. Yeah, that's good. I'm not familiar with 100% rating. I know that in regard to panel boards, switch boards, breakers that are applied in those applications. I'm gonna have to think about that one, Eddie. Utility companies can, yep. What's a snubber? I think I saw that one already. When 450.3 refers to 240.21, 240.21 does not specifically specify. It is assumed, whereas 240.100 specifies over 1,000. Why is that? 240. So I got. So you guys are answering these questions. So, okay, good. You guys are doing good on. Let me move the chat over here. These are the chats for the guys on YouTube land. NEC IEEE nomenclature grounds. For example, per AC standards, VARs and KVARs are all lower. Yeah, good point, Michael. Yeah, I try to follow that, and I may have screwed up in a few areas, or quite a few areas. I'm not as diligent. I keep going back and modifying. So, yes, good idea. I can definitely improve the PowerPoint by using the proper 480Y/277, small k, big V, big A, and putting a space in between. Thank you. I will do that. I try to apply the tap rules. Oh, secondary. Yes, secondary. You can't apply the tap rules. You got to go to secondary. Those are transformer secondary conductors. They're not tap conductors. Yes, big misconception. All right. Please submit a PI. Public input. PI means public input. Used to be a proposal. Now it's public inputs. All right. Is an inrush a curve? Isn't inrush a curve and not just a single point? 25 times at 0.01 seconds, 12 times. I've never seen it plotted as a curve. I've always seen it plotted as a point. I don't know if that's. I'm not sure about that one. I think it's so fast. I've never seen it plotted that way, or even talked about it that way in IEEE standards. Yeah, and it's different every time. 0.1 is a rule of thumb. Yes, it's been used for decades. Absolutely. Okay, 125% of full load amps of the transformer blindly. Yeah, so you know what? That's my point of the curves is to get you to understand there's a lot more to protecting transformers. We do blindly use 125% for primary, and 125% for the secondary. We blindly use some of the numbers that are in the National Electrical Code. We can do better. As I showed, I could put an electronic trip unit on that motor, on that molded case circuit breaker, and give you better protection of that transformer, because I can do more adjustments with it around the transformer damage curve. But you're going to pay a little bit more for that breaker. And you have to ask yourself, is it worth paying a little bit more for the breaker and not having to buy a new transformer? Or, I mean, you followed the code. Remember, the code's not foolproof. The code is not a design guide. It's going to create a safe installation, but that doesn't mean you might not have to replace that equipment because of fault currents. So you can go above and beyond and provide a little bit more protection, but you have to justify the cost to do that. You look at large transformers, we put differential protection, we put temperature sensors in there, we put oil, we do a lot on large equipment because you spent a lot of money on that piece of equipment. You will do a lot of things on larger equipment that you won't do on this little dry type. Number one, because it's technically you can't, but in other cases you wouldn't, because it's just not worth the cost. Primary only protection of the transformer. You still have to protect the secondary conductors. And yes, it seems that many do not understand the rules on both. Yes, and I tried to clarify that, and I was preached to by I'm not going to say any names, but one of the gentlemen on that code making panel, I tried to put some pointers in there just to say, hey, don't forget. And I was told that the code is not for the untrained individual. But I agree with you that is often missed. I see a lot of designs where they didn't put a secondary breaker and they just went with the 6 disconnect rule, and you just can't do that. And I had to put that breaker in, which created some selective coordination issues, and it just mothballed from there. If you have a code, can you briefly describe why you cannot size a NEMA contactor based on amperage and the NEMA ICS contactors? I will try if I have time. But I do have motor. I'm doing a motor section, which I could probably cover that in the motors. I'm doing motors, transformers today, I think motors tomorrow, and then generators Wednesday. Didn't seem allow for inrush. Yes, it did allow. You might have seen the secondary fuse on the time current curve. Remember, the secondary fuse doesn't have to worry about the inrush on the primary, so you may have seen the fuse on the secondary. But all of my examples did permit the inrush current. Doesn't the code require you to size the transformer for locked rotor amps for an indefinite time if there's a fire? There is a fire. Okay, good point, Ron. There are different requirements in fire pump circuits. I would have to go back to the fire pump circuits, but I would not disagree with you that if you've got that transformer, you probably do have to do something for that to make sure that you can supply that pump on inrush. Okay. Location of overcurrent secondary protection based on the length of secondary conductors to that overcurrent protected device. Yes, there are rules. Remember, that's technically an unprotected conductor. So they have rules for that secondary conductor. All right, so I'm just going to look on YouTube for my tubers. My proposal to flip 430AB was rejected. Ryan Jackson tried to flip that. Yeah, lower voltage. You know why, Brian? Here's the problem. When you've been doing something wrong for so, and I'm not going to say it's wrong. When you've been doing something for so long, sometimes driving a change to say, I want this to align with everything else, you'll get people using B when they should have been using A, because that's what they do. All right. So let's, can we plot panel board damage curves? No, Luis, Diego, we do not. So the damage curves that we have conductor damage curves. We have transformer damage curves. We have motor start curves, and there is a motor damage curve as well. I'm going to talk about that tomorrow. But we don't have panel board damage curves. We don't have switchboard damage curves. What we have for panel boards and switchboards are short circuit current ratings. And what that tells you is that you have to have a short circuit. You have to apply that piece of equipment within its rating. It's going to hold it together. It's not going to have an unintended rapid disassembly in the field. As long as you apply it with the right overcurrent protected devices at the right fault current values, it will hold it together while those devices do their job. I covered a little bit of that in my short circuit calculation, so check that video out. That's out there on my YouTube. And if you're not a subscriber on YouTube, please subscribe, because I'm going to be putting lots of stuff out there. Okay, 125 is used to load the transformer at 80%, which is where it has best efficiency typically. Yeah, you want to load that transformer. You don't want to overload it. You don't want to cook it. You want it to work for you, though. And there's a drive that says that we're not loading these transformers up as much as we probably should because of the way we do load calculations. And I've had some people put ammeters on the outsides of the building and show that the transformer is very lightly loaded. Single phase wave from, I'm not going to get into that. All right. Okay, so those are my YouTubers. So let's go back and let's take a look at the conductors, because now it's time to pick our conductors, and that's relatively simple, in my opinion. We know Article 240 tells us that we need to protect the conductors at their ampacity. We picked the overcurrent protective devices. We've sized the panel board that's downstream by picking the overcurrent device that's going to supply it. I mean, I could put, a larger panel board on a 400 amp circuit, but I wouldn't do that. I would put a 400 amp panel board. I got a 400 amp breaker. I have a 300 amp primary overcurrent device. So my primary conductor has to be 300 amps worth of conductor. Now, the reason I say 300 amps worth of conductor, because we're going to go where? We're going to go to 310. And here is what we do in 310. They say, ouch, I dropped my pen. They say to tell a good electrician, if you want to know a good electrician, you ask him to take his code book and throw it on the ground. And if it automatically opens to 31016 table, he's good. It's worth his salt. If it opens up to the index, I'd say, go find somebody else. No, just joking. Anyway, here's what we're going to do. We're going to know I need 300 amps worth of conductor. I'm going to go to 31016 and I'm going to say, what's on the truck? Right? But I'm going to pick my conductors based upon, I could throw 2 1/0s. I could throw 1 350. I could do a lot of different things. But I didn't pick the actual conductor. I'm just going to tell you need 300 amps worth of conductor. Now, if I did a smaller primary breaker, I can pick a smaller conductor. It's going to save me some money, right? I don't necessarily want to go to a 300 amp unless I absolutely have to. And why would I have to go to a 300 amp overcurrent device? If I am selectively coordinating through that transformer, I'm going to be driven to a larger primary overcurrent device, not because of inrush, but because I need, there it is. I need this device to selectively coordinate with that device. I don't need this device to selectively coordinate with that device. I need this device to selectively coordinate with that device. And to get that done, I might need a larger primary overcurrent device. And so it's good to know what your maximum is. What do we typically do? 125%. That'll save me some conductor size, ampacity size, pipe, smaller pipe. And if you have to bend it, it's easier to bend. Now, the secondary side, I've got a 400 amp breaker. I have to be protected. I have to protect the conductors at that from an overload perspective. So I'm going to put 400 amps worth of conductor. All right. Yep. So NEC section 240. So the points being made on our chat session here that I could size that primary conductor. I can bring that down to 175%. I can put, like I showed you on that fuse, I could put something even smaller. The maximum number, that 300 amps, I can't go greater. I can go anything smaller that will let that transformer energize. There's no code that says that I can't put a smaller overcurrent device down. I could put a 100 amp on there. It'll never energize. I won't violate the NEC. Okay, I just won't be able to operate it. So you've got to consider the inrush current is what's going to drive the lower side, and then work your way there. 125%, as I showed in the TCC curve, with the thermal damage, with the transformer damage curve, and the inrush, that 125% breaker fits in there nicely. All right. So panel board's only a 200 amp panel board. What if I only have a 200 amp panel board? I can go to 240.21. And if I look at the options in 240.21, they talk about primary and secondary protection. I can take a secondary conductor. It tells me what size it can be. It tells me how long I'm allowed to have that, what the length of that conductor. There are specific rules around the secondary of that transformer. So I'm at 240.21. I'm just going to open my code book because sometimes it's easier to read than the screen. My eyes, I'm getting old. I'm getting old. And you're specifically going to go to C, which is transformer secondary conductors. So 240.21C is titled transformer secondary conductors, and they have C1, 2, 3, 4, 5, and 6. C1 is when you're protecting it by the primary overcurrent device, and we talked about that already. That talks about there's limited applications on when you can have just a primary overcurrent device, right? 2 is transformer secondary conductors not over 10 feet. 3 is when your secondary conductor is not over 25 feet. And then you have outside secondary conductors, and then secondary conductors from a feeder tapped transformer. And then secondary conductors not over 25 feet long. Again, each of these has their pluses and minuses. And I think I put a few examples in here. Again, that's not over 10 feet. It has to be in raceway. It can't go outside that. It has to, end in that equipment. I can put a smaller panel board there. I'm going to put a smaller conductor. I'm going to have to meet these restrictions of how long I can have it and how I need to protect that conductor. C3 talks about over 25 feet, but again, industrial installations only, where you have conditions of maintenance to ensure qualified persons are serving. They can't be less than the secondary current rating of the transformer, and some of the overcurrent devices, ampere ratings does not exceed the ampacity of the secondary conductors. And again, if they're all grouped, so they're in the same panel board, can't have separate, dispersed. And then, and again, the secondary conductors in a raceway. So there's rules. You have rules associated with, but you can't forget there's a requirement in 408 that says it has to be on the secondary side as well. And then you have outside secondary conductors. Unlimited length is permitted, but there are, again, required. It's got to be in conduit, etc. So you can't forget about 240.21c and the requirements that you'll find there. And there's your 240.21b3 reference, which talks about taps supplying the transformer, where the tap conductor supply transformer comply with the following conditions. So you have, again, conditions. Now, so that's so another point's being brought up on our chat about transformers that have built-in overcurrent protection. That is a huge value proposition, and I'm gonna talk a little bit about that when I get to my SKM. So then you have your again not over 25 feet. This is C6 and all that good stuff. So those are the the examples from a perspective of we've covered the overcurrent protective device, we covered the conductor. Now I didn't talk about environmental. You don't typically put surge protection, transient surge protection at those dry type transformers. You'll see that up at service entrance equipment and things of that nature. This last example that I had was that this is the nameplate from that 3750 5000. So you'll see here that the impedance does not change. 5.92% impedance, but I have 3750 up here. I've got both of those. I've got AAFA. I have 48277. I've got low voltage amps, 4511 and 6014. So the full load amps on the secondary will change. The size of my breaker will have to be accommodated in that case, and my size of my conductors will change based upon those full load amps, because you got to anticipate that if they bought a transformer that's built with fans, someone is going to want to drive it up to that 5,000. And if they do, the voltages are going to be the same. The full load amps are going to be greater. My protective devices will probably change as well. Now, again, it's not going to impact your inrush currents. I'll probably be driving more current through the conductors. Trying to think of any of the reasons how that would impact me. But in any case, all right. So what I want to do before, I'd say it's 1:42. I do want to walk through this example. I want to just bring up the SKM software because we're gonna just take a look at these examples. So here's what I did in SKM. Let me just get out of the picture. All right, so here's what I did. I created basically, let me just zoom out to all. I created scenarios, 1, 2, 3, 4 scenarios here. The first scenario is basically at your 300%. So this is my 300 amp standard HKD breaker, 112.5. My fault current on the secondary, that's a good question. So let's talk about that real quick. Where's my calculator? I'm talking to you guys like you know where my calculator is. So the full load amps on the secondary is 832.7. 832.7, divide that by 0.0417. 0.0417 is 19,968 amps. So I put 2 3-aught conductors in parallel on the secondary to give me 400 amps, and I made it 10 foot long, and that puts my fault current down to 6,900 amps. That doesn't sound right. Let's take a look at my balance system study. I'm going to run it. 0 errors, 0 warnings. Let's go to my document and go to reports. Go to my short circuit. That's bus 4. I'm going to go to short circuit. And we're going to go down to the summary. On bus 4. Those are voltages. Here we go. Yep, bus 4. 208 volts. I'm at 69. 3-phase, 6,900 amps. 6,900 amps. All right. My X to R is 6. So my X to R is looking okay. I don't want to be greater than 6.5 for my breakers. So that's looking good. So now, this one is the 300 amp breaker. This one is a 400 amp. Remember, this was the electronic trip unit with a thermomagnetic breaker on the secondary. This one is my standard thermomag breaker on the primary and a fuse on the secondary. And then this one is my 200 amp. I put a 200 amp fuse. I could have put the 175. I just used the 200 amp. Let's take a look at this one real quick. Now what I'm going to do is I'm going to take a look at the plot. So I have a fuse on the primary, fuse on primary and a secondary. So primary fuse and secondary fuse. So there's my time current characteristic curve. This is my primary fuse, and I can have my inrush. I'm going to take that down. Oh no, I have a trip 125 amps. So that's at 125 amps. There's my 200 amp. So I could put 175 amp. I could put any one of these. I put the 125 amps. You'll notice if I go to 110, I'm still working at 110. I'm not into that inrush. Really good protection, but I don't want it to trip. 125 is going to do me fine. All right, so let's take a look at the incident energy on the secondary arc flash evaluation. So this is my incident energy analysis around this transformer. That first panel board on the secondary is the killer, right? So at the 300% or the 250%, the 300 amp breaker molded case, I have to assume line side propagation. So my incident energy is 13 calories at that first panel board. PD6 is PD6. Let's take a look at the panel 6. Bus 6. Hold on. Let me get back to this. What bus is that? This is 13. This is 1.48. Bus 8. Bus 8. Bus 12. Bus 8 is my CKD, my KD 400 amps. So that's the electronic trip unit. So that is, let's take a look at that one. I've got nice 1.48 calories on the secondary. Let's take a look at that time current characteristic curve. Electronic trip unit breaker, secondary breaker, open. All right, so there's my energy. There's my breaker. So there's my energy. If I increase this short time delay, my energy goes up to 3.44. That's at its longest short time delay. So somebody will, people will ask me, what does changing this set point do? It doesn't violate the National Electrical Code unless you're selectively coordinating things, but it will increase incident energy. I could bring this all the ways down, get that to 1.42. Boy, look how close I can get that. I can get it right almost on it in 1.29. I think 1.42 is not bad. So 1.42 is not bad. I can move this up if I wanted to not de-energize the transformer, just take out the secondary or overlap. I don't have to worry about coordination. I could move this further to the right, but I don't have to. I want maximum protection. I'm going to move that to the left. I'm going to move this down just above inrush. I'm going to energize that transformer. If I can live with this setting, I've got good incident energy at the secondary panel board because this is the primary breaker. So that's a good thing. Take a look at panel bus 12. Let's take a look at what bus 12 is. Bus 12, bus 8. Bus 12 is my HFD breaker. So that's the standard thermal magnetic circuit breaker. And my incident energy is again up at 13.7. Let's take a look at 7.7 is bus 16. I believe that's got to be my fuse. Bus 16, that's my 200 amp FRS fuse. So let's change that to, remember we said we could take that down to 110? See what that does. 4.4. So that's the best I could do with that one is 4.4. But I'm going to move that back up to 125. 7.7. So now, if I wanted to, we make us, our transformer guys, really sharp dudes, what they did was they took the standard thermal mag breaker. So let's take this this one here. Let's take this circuit breaker, and what we're going to do is we're going to take this disconnect. So what I just did was I disconnected this conductor, this breaker from the panel, and I'm going to clone this puppy. Clone it. See, you didn't think cloning was possible, but it is. I connect that to the secondary of that breaker, primary of this breaker. Because this breaker is now in the transformer, right on the secondary of this transformer, this conductor length is going to be much shorter. I'm going to change that to 5 foot. Okay. I'm going to leave this one at 10 foot because that wouldn't have changed. I'm going to move this stuff down. Move that up. Whoa. Move that up. So now I have a breaker that's inside of the transformer now. It's part of that transformer, separate from this enclosure. And now I'm going to rerun my fault current study, run balance system study, because I changed some conductors there. I'm going to rerun this study. And look what I did. Let's see, PD1, bus 4, right? So this is bus 8. I changed bus 8. My bus 8 is now 0.15 calories per centimeter squared. That, in my opinion, is the best design decision you could possibly make. Putting this overcurrent protected device on the secondary of that transformer, or in that transformer on the secondary, will considerably reduce the incident energy at this panel board. This is a main lug only panel board now. This overcurrent protected device, I can take credit for my incident energy in this piece of equipment by the use of that overcurrent device. And the result is the best clearing time out of all of these, 0.15. You get the fastest clearing time, which will reduce the incident energy. And that's a standard thermal magnetic circuit breaker. That's not that's a standard KD breaker. That is not a fancy electronic trip unit device. That is simply moving it from this panel board to you could put a breaker in a box. Just put a fuse in a box. We could change that. Let's do the same thing with the fuse. Take this, this is bus 12. Bus 12, there's bus 12. 13 calories, right? Take this fuse, do the same doggone thing. Go to this device and go to connections. Disconnect the secondary. We're going to take this, we're going to take this conductor, we're going to clone it. We're going to put it on the secondary, connect that. We're going to move all this stuff down. I mean, we're doing a lot of work for a 112.5 kVA transformer, but our electrical workers are worth it. And if you just made this a standard practice, you would not have to do this. I mean, if you just said, if I have a 112 kVA transformer and I'm going to standardize, this is the primary device, this is the secondary device that's going to be in a fusible switch. I'm going to leave this the same. I'm going to do run. And then your incident energy is going to be in the dirt. I mean, literally. You can work on this with daily wear, right? So I'm going to run my arc flash evaluation. I'm going to rerun my study. And my bus, what number is that? 12? My bus 12 went to 0.7 calories per centimeter squared. You got to love that. That is what it's all about. So, a simple design decision of putting, say, a fusible disconnect switch or a breaker in a box, just like we did here. I put the breaker in a box. I put the fusible disconnect switch feeding a main lug only panel board. I simply relocated the main from the panel board to a separate enclosure, or buy a transformer with everything built in, and that will considerably reduce your incident energy at that panel board, creating a safer installation, less damage should an event occur to the facility or to that equipment. Your electrical workers are in much lighter attire, and you are keeping people safe. So I'm looking at the chats now. Crash before, because if you want to get more work, you can look at proposals and comments. Okay, we're talking about public inputs. Many stop when they see the condition that meets their installation. That's right. Mr. Platt, 240.21c, 1, 2, 3, 4, 5 states that all of the conditions must be met. That is absolutely right. And we're human beings. The moment you see what you want, you stop. And that's the fact, Jack. That's the way that cookie crumbles. Okay. Going to do. All right, so I'm just looking at my program here. See if there's anything that I didn't cover that I think I should cover. We talked about the medium voltage. Medium voltage is no different. You're just using a different table. I didn't get into the medium voltage sizing, but it's the same principles that we just covered. We talked about the short circuit current on the secondary, and there was only a few more slides that looked at the medium voltage application. And again, I sized everything based upon full load amps, which is the 5,000 kVA. And that's all there is to say about that. So I am going to stop that. I'm going to not keep my things. And now what I need to do is it's 11:58. I need to show the Menti code for the exit. So give me a second. Let me find my. Oh, there it is. All right, let's see what we got. We got 400 people on YouTube. Thank you for joining us. You guys are phenomenal. Don't forget to subscribe. We got 13 likes. Smash it if you don't. Thumbs up if you love it. So that's good stuff, and it will be out there for a while. So don't worry about if you missed anything. You can always pause it and look at things. PDH, open in new window. I'm going to display, because I didn't make a slide, I'm going to display the first slide of the Mentimeter. So it is thinking about showing itself. There it is. And I am going to hit present. Thinking. All right, so there's your code, 315541. 315541. We did. I'm gonna while you have that on the screen, you can go. Remember, that's the tail end. So you're gonna just log in, put your name information, take the short quiz, and if you were following along, you know the answers to that anyway. But that's not the point. So I'm going to look at the chat session. I'm going to look actually on YouTube land, because YouTube land. What are the questions there? So I'm gonna look at the dialogue. I love the fact that you guys are chatting away. It's my proposal to flip. I saw that. I understood that you can use 6 disconnect rule on the secondary as long as the total rating of the breakers does not exceed 125% of the full load current. You got to remember, panel boards, That is a different story. And in reality, I can't figure out when. And there's probably an example of what you're supplying, but if it's a panel board, you are not going to be doing 6 disconnects on the secondary unless it's a service entrance equipment. You're downstream, service entrance, we've got specific rules there. We've got line side barriers, etc. Okay. States all the conditions must be met. Noted. Yep. Thanks, David. We'll be live streaming the next 4 Wednesdays as well if you're interested. Excellent. Yep. Nope. Good. Hey, Ryan. I know the more people that are doing this stuff, the more opportunities for knowledge. I've got a lot of our busman guys. They're going to be doing presentations as well. I think Mike Holt does something in the evenings. You're doing the stuff. So, keep this. This is all good stuff. Sharing knowledge. That's what we got to do. 220 AC removes 2 to 6 overcurrent protective islands for panel boards. That's right. That's another key thing, Ryan. We removed that 6 disconnect rule. You're no longer going to see a panel board, even at service entrance equipment, with 6 disconnects in it. Yep. Individual disconnects, each with their own set of secondary conductors. You can use the 6 disconnects permitted by 450.3. Well, thank you, Dawn. 6 individual disconnects, each with their own set of secondary conductors. That's I might draw that one up. That's a good application. Thank you, Dawn. All right, I'm looking at YouTubers. All right, so let's look at the chat. Remember, for everybody out there in YouTube land, follow the Menti 315541. That's the number that you are going to want to use. 315541. All right, but are they going to sign the checks to PPE? Are they going to sign the checks? I'm out of that discussion here. But the design decision increases cost, which is frowned upon. Hold on, let's think about that. So I don't. You know what? I've not done the cost analysis on your. You don't have a main overcurrent protected device. You remove the main overcurrent protected device out of that first panel board, and you put it in the transformer. I'm not sure what we charge for that transformer. I'm not in sale. I'm not a numbers guy from a sales perspective. I'm a technical guy. And if you did a main breaker outside, you might increase that. I'm not sure by how much though. So just keep that in mind. Our electrical workers. That's one of the most dangerous places in any power distribution system is that first panel board on the secondary of a transformer. We can make people's lives a lot easier. And if they do it in the design and make that a design part of the basis of design, and you get the customer, the consultant, or you get the architect to specify that, then everybody's going to bid it, and that'll drive the price down too. Competition's good in this world. Are they going to sign the checks to PPE? It's true, and the time and the damage. Remember, reducing incident energy is an important part of the design, because I know we love to say we don't do justified energized work, but voltage monitoring is justified energized work. A lot of people will turn the main off in that panel board, and that really doesn't isolate that panel board. They've got to go upstream to kill power to that panel board. A lot of times that doesn't happen just out of necessity. Reliability, if it's an industrial facility. Unfortunately, we have a lot of people not practicing establishing electrically safe working condition. So it can reduce incident energy. It can increase electrical safety. It will reduce your downtime should an event occur. I mean, if you don't care about the electrical worker, you're probably going to care about uptime. We should all care about the electrical worker, because if we're keeping him safe or her safe, our power system reliability is going to go up as well. And what we did with the transformer, that breaker in transformer, we call it a BIT. Remember, 315541. Let's do an Eaton. BIT. Breaker integrated transformer. Low voltage, dry type transformers. This is a this is the website for that. I tell you what, in my opinion, I love this stuff. I love this equipment. What we did was we increased the height of the transformer. So we didn't increase the depth or the width. We basically integrated that transformer, integrated the breaker, and there it is. So it's a little taller. So you know what's nice about it is your beer will be a little bit closer to your chest area when you're standing in front of it, or your coffee. We're not supposed to put anything on top of these transformers. Okay. I mean, I told those that they need to do is make like a teepee on the top. You'll never set anything on top of a transformer. We have new code requirements to tell you that. But in any case, that's basically what we did there. We can do it on the primary and secondary, but the value proposition there is much lower incident energy downstream. And I think that is makes your life a lot easier, and it will increase electrical safety and all that jazz. All right. So let's see what we still have on YouTube. We're down to 348. All right. Let's see what we got. If you supply 6 individuals, all right. Don't forget the 315541. Take the quiz. Don't forget about, I'm not a sales guy, but I love that product. And not too many. I learned about this product talking to a customer, and we came up with this idea at dinner. And I went back, I had my engineering services guy. I said, you know what, if I can't get the product line to make this, services, you guys can make it, get it listed, and sell it from the services division to these big industrials. I'm a genius. So, we were. So I sent an email down to the plant and said, hey, I got an idea. I went through the whole story, and I got an email back and said, hey, Tom, we come up with that 2 years ago. So that's how I got educated on this. But it's probably, I think, one of the best kept secrets that we've got at Eaton. Very cool little product. And again, smaller wires on the I never thought about that, Ryan. You know what? That's a good point. So Ryan Jackson is saying that integrated overcurrent protected device, the BIT, will allow smaller wires on the secondary, since we need not worry about 240.4b, the next size up, being disallowed. Interesting. I like it. I got to put that example in there too. So this is all great input. I appreciate. We're 8 minutes over. We had a great 2 hours. And everybody's hanging in there. I really appreciate that. If you find value to this stuff, please let me know about it. Share it with other people. I've got this week lined up, and I'm already thinking about Thursday. If you are a petrochem, if you're a hazardous location, I've got a guru on Haslock who's going to do a presentation for us on Thursday. I'm not going to be the presenter. I'm going to be the host. I'm going to be making it work. He is going to present from our Crouse-Hinds division. So you don't want to miss that one. And depending upon how much he gets done, I may have him on again. So, but in any case, tomorrow is motor protection, generator on Wednesday. We're doing Haslock on Thursday. And then on Friday, I was going into more incident energy and arc flash. And I'm thinking next week, I should have done conductor protection on Friday. This would be like the protection week. It would have been cool. But no, I had to go uncool. So I moved over to do, I just wasn't thinking. Monday, I think I can't next week. So next week is another bad week for me. Last week was a bad week for me. Next week's going to be a bad week for me, but it's going to be a good week because I'm going to be off that week again. And you guys can watch me put my bed on my truck on YouTube if you want. But the week after that, I'm going to be lining up, and we'll do conductor protection the week after that. If you have any other ideas on what types of sessions you want like this, let me know, because I'm going to start tapping. Hopefully, I'll start tapping some other people in our divisions. or maybe some external help. You know, you never know, Ryan, or my buddy David Platt. We might be doing something together one day. So, and anyhow, cool beans. Thanks for tuning in. Appreciate the attention. Appreciate your feedback and all of the notes and chats in both the WebEx and on YouTube. I'm going to go to the outro. And thank you, Don Ganir, and thanks everybody. And Nihad, you guys, 250. Excellent. I'm going to go to the, for the guys on YouTube, I'm going to the outro. But if you stick around, I'm probably going to come back live again. But I'm just going to cut, I'm going to cut it out and go to outro. Thank you very much on YouTube land. All right. Man. Okay. Control T, Control Q.